Hello, my name is Jakob. I would like to present the project on estimation of stereophonic source panning parameters. I work in the audio analysis lab at Aalborg University, where this project has been carried out and is a project in progress. I'll give you an introduction to the problem. I'll explain the signal model, some proposed method, experimental results, and lastly a conclusion on it. So why do we estimate stereophonic panning parameters? It's because improvements have been shown in research on multiple fundamental frequency estimation, as shown in reference 1 and 2 here in the bottom. Also, improvements for source separation and signal enhancements, among others, are possible. Stereophonic mixtures is something we observe, for example, in TV broadcasts, in radio broadcasts, etc. Therefore, it's a very widely used format. So we propose to find the number of sources and the stereophonic panning parameters related to the sources. So what is a source? If we look at the figure here for a stereophonic configuration, we have a left speaker and a right speaker, and one source in this example, called virtual source, which can move on an arc from the left to the right speaker and vice versa. So phi k is the angle to the virtual source when the listener is observing is facing the x-axis. We model the mixture Ym in channel M at time instance n as a sum of k attenuated and delayed sources. The attenuation gain ratio is called gamma for the k source in the M channel. The source is called Sk, and the delay is delta for the k source in the M channel in samples. The gain ratio here, gamma mk, is based on trigonometric functions because the trigonometric functions has the quality of giving us a constant distance to the virtual source from the listening position. N, capital N here, can be defined as a segment of the full recording. For music, it's very often we have used 600 milliseconds, and it's possible to use large frame sizes compared to, for example, speech, which is very often smaller frames. For each signal segment, the observation x is shown in equation 2. This is the interaural level and time differences. It's computed from the Fourier transform capital Y of each channel, so it's a ratio between these, which gives us gamma, an estimate of gamma called gamma hat, and tau hat. This is a function of frequency in the DFT. So x is every observation of x is a two-dimensional vector. The narrowband assumption limits the maximum frequency and the maximum delay that we have applied in the experiments, and also the assumption of W disjointness is shown here. This is a very widely used assumption, which basically says that source K and source I does not have spectral overlap. Since this is not the case amongst other assumptions also violated, we see here the distribution of X is in this example we have 3 sources, and we can see that these are not point-wise estimates. What we can do this, and what we also have done in the experiments, is to apply a threshold. In equation 3 we see the indicator function B of W, which is basically a threshold set related to the signal power. This gives us a much faster computationally algorithm and also removes part of the noise floor. So how is the number of sources and their panning parameters estimated? We proposed the method at ICASSP 2018 in Canada, which is a method based on clustering of the observed interaural level and time differences. We use the generalized variance and the posterior membership for selecting clusters across all segments. We parameterize the observations as an unconditional distribution model shown in equation 4 is a probabilistic model of finite mixtures, namely a Gaussian mixture model. Theta is the parameter vector, where we have the parameters alpha, which is the mixing probability, which means it's the probability of having the class K. Mu is the mean, which is directly related to the panning parameters that we want to estimate here. And C is the covariance matrix estimate. We assume in the full recording that the stationary panning parameters, which means that if we have, for example, in a music mixture, a drum set which is in mono, and we have panned that to stereo to some position, we assume that position to be fixed through the full recording. Once that is done, we observe IID samples, independent, identically distributed, where xi is one observation in the equation 2 of the ith signal segment, and the log likelihood function is then shown in equation 5. Such parameters are estimated as the maximum likelihood, and the GMM is implemented as an EM algorithm. One of the qualities of the Gaussian mixture model is that it can model arbitrary distributions as a combination of components. So therefore, it's very prone to overfitting. A widely used method for solving overfitting is the MAP estimator, the maximum a posterior estimator. In such an estimator, there's a penalty term on the prior of the parameters. One example of these is shown in the figure, the Bayesian information criterion, as a function of the number of sources. Each graph and each color represents a different restriction on the covariance matrix. What we see here is a monotonous function for every restriction that we have, and there is no peak that we cannot minimize this estimator or this cost criteria. Therefore, some of the challenges are summarized here. Does not necessarily exist a unique definition of a true cluster. You might see something, I might see something else if we look at some distribution space. The assumption of normality does not exactly hold, and also the W disjointness is violated even for speech, as shown in a reference by Scott Rickard, reference number 4. The GMM can model any distribution as a combination of components, and if we look at this figure, the black ellipsoid shows this overfitting quality. This is the MMDL method of reference number 5, and we have 10 black ellipsoids describing a mixture of 3 components. Therefore, we propose to overfit on purpose and then locate the clusters from the candidate set. We find the number of sources in the set indexed by S from 1 to capital S, and the estimated parameters theta S is ranked such that beta 1 is smaller than beta 2 up to capital beta S, beta capital S. And beta is chosen to be the generalized variance. The generalized variance is computed as determinant of the covariance matrix. And after we have ranked the parameters, we compute the posterior probability of xw belonging to component S, which is shown in equation 8 as zeta. Here we can see that the first column is related to the S component, the first component, and the second column to the next component, and each row in zeta is related to frequency. If we go forward in S from 1 to capital S and check for unique observations, we can then use that for finding the number of components. So in this example I've shown some numbers. A unique assignment is a column of only 0 and 1s. So it means if there's a 1, that observation has been assigned to that specific component with 100% probability. In this example we can see there are 2 clusters, because in the third column we have a number between 0 and 1, which means that this specific observation is assigned to 0 clusters. Therefore, we choose the first 2 columns as the first 2 clusters, the only 2 clusters. This can also be described as shown in the bottom here. There's no need to go into detail with that. This is how we can find the number of sources in the 3-source example showed previously, where our method has been applied, and which is shown in color here. as a Gaussian mixture model. Here's the experimental result on the ranking of the Gaussian mixture components. This is a comparison between alpha, the mixing probability, and beta, the generalized variance. For each iteration, k is 4, which means we have 4 sources. We can see a great improvement in this case from 0.2% to 99% in this, approximately in this case. Which means that after ranking with the generalized variance, we will have the first, we have located the clusters as the first sources. The panning parameter estimation results are shown in the table here. On the EBU SQAM CD in 1000 iterations, we have set a mixture randomly 2 up to 5 sources has been randomly mixed together, and we apply our method and have a precision rate of 93% and a recall rate of 88%. That was the last experimental result, and now I'll conclude on the ICASSP proposal. We have proposed a blind source panning estimation method, which determines the number of sources, as shown from the precision and recall rates, based on the generalized variance and the posterior probability of the assignments. The parameters distribution is modeled as a Gaussian mixture, and the method was based on clustering of interoval level and time differences. And we showed promising performance in the experiments where we used the EBU SQAM and the Iowa dataset, which contains anechoic and also various music ensemble samples. Thank you for listening. And please feel free to contact me on email if you want. So additionally to this, there's a source separation example, which is an extension of the ICASSP proposal. We propose to take the statistics that we have obtained from our method, where we have estimated the number of sources and the panning parameters. So we take these GMM components and fit them to every frame of a short-time Fourier transform. So we compute a short-time Fourier transform, and for every frame, we re-estimate alpha and C. Then the zeta is a soft mask for each frame in that short-time Fourier transform to map out the different frequency components of the signal, and then run an inverse short-time Fourier transform. And that will give us the k estimated stereo sources. So it'll give us, if we have 4 sources, it'll give us 4 stereo tracks. So I want to show that in as a proof of concept audible example, where we compare to state-of-the-art algorithm shown in reference number 7 in the bottom here by Alex Osirov and Cedric Fevaux. We have an observed mixture containing drums, bass, vocal, and other track, which is everything else than drums, bass, and vocal. These 4 tracks was mono and has been, and to these tracks we have applied our panning model showed here, with only amplitude panning and no delays, to be fair to state-of-the-art. Here is the observed mixture playback. Okay, and here's the results. Everything to the left is the state-of-the-art NMF method, and everything to the right is our proposed GMM method. All the graphs here, they show the blind source separation evaluation metrics, the signal to distortion rate SDR, the signal to artifacts ratio, the SIR, and the ISR. Every color for the graphs is shown in blue is a bass, every red graph is drums, every purple is vocal, and every yellow graph is everything else, which is the track called Other. The general trend in the graphs is that in this case, on the track called Angels in Amplifiers, I'm Alright, our method performs better. Let's listen to the results. Here is the drums. I'll first play back the state-of-the-art and then GMM. And the now method. So it's quite easy to hear that what we can hear here is that our method has more emphasis on the high frequency content and a more continuous sound to it. That's my interpretation. Also, the bass drums, it's better in the NMF method than in ours, and there's more emphasis on the attack, but namely on the attack, and that's also what we can see in the graphs here. Let's listen to the bass, which has the same qualities from my interpretation. So it's quite clear that the NMF method has more bleed on the bass. Yeah, that's very clear. Let's listen to the track called Other. So the GMM method just sounds much more high frequency smooth, and still you can hear that what was missing from, for example, the bass drum in the drum track was maybe bled into this specific track. Let's lastly listen to the vocals before we end the presentation.
I'm alright, get away from you, and I'll be fine. Cleaning up the corner, put it back in order. But no, I will always have this too, a little piece of you. I'm alright, get away from you, and I'll be fine. Cleaning up the corner, put it back in order. But no, I will always have this too, a little piece of you.
That ends the presentation for today, and thank you very much for listening, and please feel free to contact me. You can find my email on Aalborg University's webpage if you wish. Thank you.